Hi, everyone. And my name is Akanksha, and I'm from the marketing department here at C&D Technologies, part of the Zappi group of companies. I'd like to welcome you to our panel discussion with Flux Power and Trojan Battery. Please remember that this session is unrecorded, and we will be able to watch this on demand following this session. I'd like to welcome you to our panel discussion. If you have any questions, please add the Q&A tab that you can find on the two parts of your screen. Note that your answers will be sent quietly. Please add the Q&A tab that you can find on the parts of your screen.
Gotcha. There's feedback and echo.
With that, I would like to pass it on to Rod Darrett.
I think we are good.
With that, I would like to pass it on to Rod Darrett.
Thank you, Akanksha. Appreciate the introduction. My name is Rod Darrett. I'm the Director in Business Development at C&D Technologies. And alongside, we have John Kopera from Trojan Battery and Paulus Geantil from Flux Power. So, John, maybe you'd like to make a quick introduction?
Yes. I'm John Kopera. I'm here with Trojan Battery, and I'm responsible for the electrical engineering of the lithium products that we develop here. We recently introduced our lithium product for the golf market earlier this year, and so very pleased to be here and participate in this discussion.
Yeah, hi guys. My name is Paulus Geantil. I'm the CTO here at Flux Power, and I come from a background of physics and embedded software, firmware. And so Flux Power is one of the first companies to bring lithium technology to the material handling industry. We also do automated vehicles and energy storage.
Perfect. So before we get this session started, Rod just had some technical difficulties. So he will be rebooting and I am going to just take over. So before we commence, would you like to just give a quick overview of what your companies do?
Sure. So C&D Trojan is been around for about 100 years or more than 100 years, and has a large business manufacturing lead acid technology, which is used in a variety of markets: stationary power, motive, material handling, the full gamut. Recently, we have decided to introduce a aftermarket lithium product. We have developed lithium for stationary power in the past, and will likely do so again. But we are focusing on our motive product line right now. And as I mentioned, we just introduced the GC2 size 48 volt lithium battery into the market at the beginning of the year. So far, everything is going
Great. Thanks for that. And Paulus, maybe a little bit about Flux Power?
Sure. Let's see, Flux Power, we must be on the order of 12, 13 years old. Was initially focused on early automotive development, and Flux developed battery management technology, a modular system, and had a source of lithium cells that we would package together for various automotive projects. And for instance, the Green Tech Automotive was one of our early customers for airport electric vehicles. We then transitioned to material handling, say about 8 or 9 years ago, and started bringing products in for walkie pallet trucks, and then moved on to the larger sit-down counterbalance trucks, as well as making inroads into the GSE market. That's ground support equipment for airports. So you find our product in lots of Fortune 500 companies, many beverage distributors, and then also some of the airlines have started making that transition toward lithium. So things like belt loaders, the baggage tugs, pushback tractors, and I'm not sure what they call it, the scissor lift that lifts the container of snacks up to the airplane, all that kind of stuff.
Great. Appreciate the introductions to both of your companies, and thank you for participating in this event. I think this is a session that will be very helpful, and it'll get the conversation going to OEMs and customers that are looking to electrify, because there is so much development and design around applications that are electrified via a battery source, right? I guess let's start off with you, John. Could you kind of walk through some of the preferences of lithium solutions that you use? I mean, in the industry, we hear so many different types of solutions out there, from NMC to iron phosphate. From solid state and whatnot. So maybe you could just walk through some of the technologies on the lithium side that Trojan is looking at using currently and into the future, and why.
Okay, so yeah, as you're right, there's an alphabet soup of lithium technologies out there, and one of the considerations that we have is, of course, they all have slightly different voltages. There are different amounts of safety factor involved with the different chemistries. Also, some are more lend themselves better to a certain form factor than others. But right now, we primarily use iron phosphate chemistry, and one of the reasons for that is it is a very safe chemistry, and safety is one of our key metrics that we hold to, particularly for consumer applications. And so that led to that choice, as well as the fact that the voltage range that iron phosphate operates in is very close to the voltage range that optimally is used for golf applications.
Got it. So that sounds like it's something that is catered more towards the industry that you're trying to service. And it does lend itself to trying to understand what the requirements of the environments that you're going to be servicing in the selection of your actual cell technology.
Absolutely.
So appreciate that. So Paulus, I guess that also that same question to you, because you service from different industries that you had mentioned during the introduction. What's the preference on your side, and why?
Right. So in the material handling industry in particular, you'll find two separate chemistries, both NMC and iron phosphate. At the moment, Flux exclusively uses iron phosphate. Some of the same reasons John mentioned. The voltage range lines up almost perfectly with the lead acid voltage range. So when you're trying to do a drop-in replacement, you don't have to compromise on the range in which the equipment's going to operate. Also, we don't need incredible energy density and compactness in the material handling industry. In fact, we have to add counterweight. So once one switches to lithium, if it's going to be a drop-in replacement, typically you're adding 800, 1,200 pounds of steel ballast. And so going with a lighter chemistry, which is lighter, more dense chemistry, generally you lose a little bit on your safety factor, and then you have to add even more weight. Iron phosphate is a very robust chemistry. capable of really high cycle life, and if treated properly, that can be extended. Also, it's less expensive if you can stay away from the cobalts and the nickels. These minerals, they tend to be expensive, or often they're conflict minerals. So we're worried about the ethical sourcing of those. And iron phosphate, it has made, some would say it's made a comeback. Even Tesla now is offering vehicles with iron phosphate packs. So you might not get as much range, but you get a much less expensive pack that's probably going to last longer. So the total mileage throughput would go up on something like that.
Great answers to the question, and it's good to get different perspectives because there are some common industries and markets that you service, but there are a vast difference as well. I mean, it sounds like it's a good segue to actually the next question. And Paulus, you kind of touched on it a bit, not so much on the commodity price, and we'll get to that in a little bit, but more so on the weight for material handling, right? So there's a bunch of different cell form factors out there in the market. You hear of the 18650, which is a cylindrical cell, and the variants of it, and pouch and prismatic. Now, you had mentioned that you usually have to add weight, and the voltage that you're using on iron phosphate matches well with the lead acid replacement. So, with that said, what's the preference of form factor that you would use in your battery packs, given the fact that you do have to add weight?
No, that's an excellent question. So at the moment, the 18650 by far is one of the most popular cell sizes. If you look at iron phosphate, there's a 26650, which is also very popular. There are numerous companies making iron phosphate 26650. Also, A123 had pioneered the nanophosphate in a 26650 and 18650 form factor. And they're also very configurable. So with those form factors, you can have almost any kilowatt hour size with any voltage. In material handling, we've mostly been using prismatic cells that are roughly of the 100 amp hour size. And one of those reasons is there's simply fewer pieces to put together. And typically for material handling industry, you're looking at several 100 amp hours of capacity for something like a 48 volt system. Typical size would be 48 volt 400 amp hour, 48 volt 600 amp hour, or 800 amp hour. And so we don't need to divide down as fine as those cylindrical cells would give us. So that's one of the thoughts there. And there are numerous companies also making I don't know what to call the standard. There are a few standards floating around, but it seems like there's been some consolidation on the size and shape of these prismatic 100 amp hour cells. Some are called 105, some are called hundreds, but that allows us to do multiple sourcing without a lot of redesign. So far that's been our preference.
Got it. And John, likewise to you, I know that your primary industry that you're trying to service is the golf industry. And with motive applications, it's kind of the opposite, right? They're trying to reduce the amount of weight that is added onto the vehicle so you could get extended range and whatnot. But yeah, maybe you could comment on what you guys are looking at in terms of form factor.
Sure. I'm really the weight reduction comes because they're switching from lead acid batteries that are traditionally used to the lithium, so they save a lot of weight there. Yep. But in the form factor that we prefer is cylindrical at the moment, because it is very configurable. We have some excellent technology for packaging those. It increases the safety factor, in our opinion, because it reduces the likelihood of propagation if anything should go south on one of the cells, say it has a short or something like this. So we think it makes for a safer package. And again, it's very configurable. You can make any form factor you want really out of those cells. So that's the primary reason that we have picked a cylindrical format, as well as they have excellent cycle life because they have the can that keeps the compression of the electrode stack very consistent.
Got it. Got it. Yeah. And like, I'm fully aware of all the battle of form factor. There's not one that's specifically being preferred in the marketplace. And we see it, right? Like Tesla's heavily into the cylindrical, but then you've got GM and other OEs looking at prismatic and polymer, right? Pouch cells, right? So there's benefits to each one of them. But I guess in the case of pricing, and both of you guys had indicated that you guys utilize LFP, but is there a benefit in pricing going from one form factor, cylindrical versus the prismatic? And John, maybe let's start that off with you.
So I think cylindricals would generally be less expensive because they're easier to make than a prismatic cell. And the other thing is that, of course, LFP is far less expensive than NMC because of the lack, as Paulus mentioned, the exotic minerals that it takes to produce those cathodes. So there is, however, everybody ignored LFP for a long time, and now everybody is in love with it. So that's putting some pricing pressure on LFP. So the difference between that and NMC is not necessarily as big as it used to be. And the other thing is that with NMC, of course, you got more energy in the can, so you can use fewer cans. So there's a little balancing act that you have to pay attention to there. But in general, LFP, yes, is less expensive, but the world has taken notice of it, and so that it's becoming more supply constrained, and that's posing challenges. Just like electronics and everything else, the supply chain for all kinds of different applications and markets has gone crazy recently. So it is producing pressure on pricing, along with geopolitical factors like tariffs and other things. But in general, that's where we stand for the moment.
Got it. And I guess to you, Paulus, since prismatic is the form factor of choice, yes, you are using LFP, but is there like big effects to the actual commodity pricing as it relates to prismatic, because prismatic is not as highly produced as a cylindrical cell is in the marketplace right now?
Yeah, let me see how to answer that. What we're seeing is the per kilowatt hour pricing at the moment, as of about 2020, 2021, LFP was around $80 per kilowatt hour. NMC was about $110 for a kilowatt hour. So that's where, like John said, it balances out a little bit. But yeah, cylindrical cells, they are much more consistently manufactured. Those machines spit them out very quickly. They can be arrayed with and it's a rolling process, so it's really well suited to automation. The prismatic cells, they're sort of folded back and forth, so it's a slower process to make these cells. But what we're seeing, especially in China, with the regulations that state that all buses will be electric, this kind of thing. So many companies are sort of consolidating to certain sizes of these cells, and so really those differences are sort of going away. We're really seeing that it kind of washes out, and roughly the price per kilowatt hour is about the same. Of course, there are automated processes to build modules and things out of these larger cells. So as that stuff comes online, it saves costs down the line.
Got it.
Yep.
Good. Well, that's definitely good feedback from both sides, and definitely makes sense. I'm actually happy that both of you guys are using LFP because it's easier to navigate. I know NMC right now, or any of the oxide-based solutions, whether it be NMC, NCA, right? Cobalt is really at the forefront, and cobalt, like you had mentioned, is mined in some non ideal areas where there's situations where it's not really the ethical practices are basically being in place. But I guess with that said, and it's interesting that John, you at C&D Trojan are implementing cylindrical, and Paulus at Flux Power is implementing prismatic. Now that newer technologies are frequently discussed in the marketplace, solid state batteries per se, those are both, or not both, but those, from my research and understanding, they're developed on polymer pouch based solution. I guess, do you guys have any input as to what you have done thus far, if anything, related to solid state, or any new technologies in our forefront with respect to lithium cells? I mean, either one of you guys could respond to that.
So we always keep our eyes open and the ear to the ground on the new technologies. At the moment, solid state is, in my opinion, not ready for prime time, and the ones that do seem to kind of work are really specialized application batteries, and not for general application, right? So it's going to take a while before they get to the level of being a broadly commercial product with these cells. The other thing is that we have to wonder what the definition of solid state really means in these batteries. Does that mean really that it's a solid state battery? Usually no. Usually it's got some sort of solid polymer electrolyte, but it also has some sort of liquid in it so that the cathode still conducts. So is it really solid state? Maybe, but maybe not. The other challenge is some of them are using metallic lithium, which has its own issues of handling and dendrite growth and things like that that still remain to be solved. There's some technologies using silicon that are very interesting. Unfortunately, the problem with silicon is it doesn't have the greatest cycle life. So, there's all these different technologies and they all serve a purpose, but at the end of the day, and this is pretty true, no single technology in the battery industry has ever completely supplanted another one. There's always somewhere where there's a technology that's really the best for that application.
Yep. Paulus, do you want to add to
that? Sure. Yeah. I largely agree with what John's saying. I did attend the Advanced Automotive Battery Conference this year, and the one group that said that they had something working in the solid state, their battery was something like 20 thousandths by 20 thousandths of an inch, and it was really ultra tiny, but they were trying to solve these problems of cracking and just there's a lot of issues trying to get that to work. There are a lot of technologies, as you mentioned, LFP, iron phosphate, the NMC, nickel manganese cobalt oxide, LCO, which is kind of the original lithium electrolyte. So it's in your cell phone. That's really one of the most volatile ones. It's funny that nowadays everybody has one of the most volatile chemistries in their pocket. Lithium titanate oxide is an excellent chemistry, but it's really expensive. You've got to put titanium in there. It's got massive cycle life, but one of the problems, the cell voltage is very low. And so, yeah, so it lends to its own problems, but it does have its uses. And then as we see NCA, or nickel cobalt aluminum oxide, that's been a big push with Tesla and others, because you can get such great energy density. But that comes with other risks and cooling requirements, or I should say thermal management requirements. So really, when you take a look at all of this, uh, in addition to that, we can read articles every week about something new coming from a lab, and it takes years and years for that to really hit the market. Lithium was invented in the late '80s and came in the early '90s, but here we are, 2022, and it's largely available. So it's just kind of a lesson for a new technology to become largely available. It is years away, and one of the problems is, as soon as someone discovers something a little better, a little newer, by the time they start spinning on that, something else has been discovered or invented, and it's kind of this whole whack-a-mole game. Iron phosphate is reliable. It's been around a long time. It's very well understood. Um, it is great cycle life and a convenient voltage range, and they are making advances in the energy density of it and the longevity, either through additives or sometimes coatings, purifications, different electrolytes. So there's still work going on there. It's good to see it resurge a little bit. For a while, companies were showing me their 10-year roadmap, and they were all planning on phasing out iron phosphate. Now, every one of their roadmaps, from what I can tell, shows the growth of iron phosphate going along with everything else, and that does constrain, the supply. So, we've seen a nice decrease in price since the '90s, something like a 90% decrease in price of lithium. But that trend is not easily continued. New mines have to come online, and the demand, and for a mine to come online, the demand has to be high enough. So there's almost what do you call it, kind of a wave-like pattern of pricing as we go forward here. And of course, the pandemic has caused problems with the supply chain. So we're looking at the short term. We're probably looking at roughly a 20% increase in some of these self-suppliers products. Some of the news I'm hearing. So there you go.
And we're seeing a lot of that cost being passed to the consumers, and so we definitely understand that it's a problem that needs to get resolved, right? Because supply chain constraints are pushing the boundaries, as well as sourcing the actual raw materials for these cells to be created, are because the demand is or the supply is not meeting the demand. The prices are starting to skyrocket. But with that said, because both of you guys are looking at a short term or medium term into LFP, are there any other technologies outside of LFP that you guys are considering at this moment? Not in the short term, but in the medium to long term. Do you see certain chemistry taking precedence over LFP in the mid to long term? John, maybe.
Well, that's a good question. Basically, the choice of chemistry, as I'll reiterate, is really based upon the application requirements.
Mhm.
So if we have an application that, like, for instance, our golf product that is a aftermarket product that it exists in an arena that used to be served by lead acid, then LFP is the obvious choice. If we're going for an application where you have to get as much energy as possible in the box, we're going to pick something else, because LFP has got fairly low energy density. And then it's going to be constrained by the application's voltage window. How much power does it need to draw from the battery for a given volume that the battery can occupy? So all of these things will drive the choice of which technology we're going to use for a particular application. So we don't write the other ones off, because they all have their purpose. But right now, for our initial market of aftermarket GC2 style batteries, LFP is the choice.
Got it. Got it. And Paulus, maybe you comment because yours is a little bit more power dense, heavy needs and requirements, and likewise, cycle life is um, definitely a big requirement on your side. So I think more in the markets that you're servicing, it requires that good balance of energy density and power density, right? To be able to surface or to provide solutions in the market. So maybe LFP would work for now. And I know you said that there's advancements with LFP, but are you looking at any other type of chemistries or cell technologies or improvements to the current solution you're using right now?
Yeah. No. So yeah, we do. We just like John said, you have to what fits the application. So some of the applications, for instance, um, warehouses that operate 24/7, and so in that warehouse, uh, when they used a lead acid solution, sometimes they would have a wall of lead acid batteries, and that wall has chargers. There's some sort of changing equipment there, and the driver would come in at the beginning of the shift or at the end of a shift, swap out the lead acid battery for a new one, and then plan on trying to run that 8-hour shift on that battery uh, until the next shift. And the idea there was 8 hours of charging on lead acid, 8 hours of rest, and then 8 hours of use, and then repeat. Um, so when we bring lithium in, um, part of the idea there was you could do opportunity charging. You can charge a lithium battery faster and not heat it up as much, is one way to say it. And so now that operation becomes there's a 15-minute break, a half-hour lunch, another 15-minute break, and then a shift change. And we co-locate the charger where the work area is or by the break room. And so those operators plug in and do their opportunity charging. And so you have roughly an hour to an hour 20 to charge per 8 hours of runtime. And so now what you find is you actually don't need as big of a battery. The battery has to support the charge rate. We call it C rate. So if you plan on, uh, you know, so the short of it is the charger is really what keeps up with the work. You've got to replenish the energy you're using each time you charge, but the battery can only accept so much energy for its size. So that puts a constraint on how small that battery can be. So we size the battery appropriately so that we're not charging at too high of a C rate, but also we're not trying to put so much lithium in there that the battery's too expensive. And then you're trying to maintain that state of charge of the battery somewhere around the middle. So you really don't want to go to 100% and come down to 70% and go back to 100 and repeat that. That wears out the battery if you cycle at the extreme ends of the SOC range. So in an ideal world, you would cycle that battery, say, from 80% to 20% back and forth throughout the day. And your opportunity charge, replenishes what you've used enough to get through the next portion of the shift, and that repeats. And then we find if we can get that figured out, that you get a very long lifetime on a lithium battery in that sort of application. And it keeps up with the work. Of course, you're typically putting in a larger charger. Some of these operations you're charging more than 300 amps, but it depends on the application. If you're picking up chips, potato chips and things, these are not really heavy. If you're picking up, engine blocks, then you're working that truck a lot harder. So you'll need more energy replenishment. You might need a bigger pack in that application.
Yeah, very load dependent.
Right. So we do keep an eye on the other chemistries. If we find an application where someone needs to work a longer period of time and it's just not possible to do this opportunity charging, then you either need more energy density or a larger pack. And so obviously there's a point where iron phosphate, you filled the entire box and you don't have enough energy. Now you've got to switch over to NMC or one of the others. In material handling, the two right now are really LFP and NMC.
Got it. I guess let me take a step back then. So when a customer comes to either one of you and and they are looking to utilize a lithium ion battery in their solution. What are some of the qualifying points that you look at in terms of their requirements that lead you towards an LFP tech solution, or say that you might need another solution, like you said, LTO or lithium manganese oxide or LCO or whatnot, right? Are there any qualifying questions that lead you to say, yes, LFP is a solution that is aligned with your requirements, or no, you might have to move to another one? And maybe John, you can start off.
Yeah, I guess one of the first considerations is always how much is it going to cost,
Right.
and that's a very important thing to the customer, particularly OEM customers who are trying to keep their costs as low as possible, so that that their product is appealing to their customer as well. So it's a little bit different when you go into the OEM rather than the aftermarket, because some of the requirements, are specified. And one of those things is going to be, what's the cost per kilowatt hour? What voltage is it going to operate at? How much energy do I need in this box? And how big can the box be? So all of those things will determine the choice of chemistry. And at the end of the day, LFP usually wins.
Paulus, do you agree with that?
Yeah, no, I 100% agree with that. Often we will simply do an energy study, and so if the customer is operating now, we can put data loggers on the equipment. We can have a look at, what is the energetic usage of that application, and then once you see that, we basically have a table. We can go look at this table and figure out what size battery they need, or does it exceed what LFP is capable of. So that's generally how we do it.
Are each of you willing to go outside of LFP if needed, or is that just the standard that you guys are looking to implement? Since it does have a lot of the benefits that you both
Sure.
mentioned.
I mean, sure. We have, for instance, developed over the last 15 or so years several products that are not LFP, that were designed for stationary service, telecom applications, and other standby service. So we've definitely explored other chemistries, and they work quite well for the Gulf aftermarket, as I mentioned, for some of the reasons that I mentioned, because we're going into a lead acid replacement market. LFP was the obvious choice, as well as LFP being substantially less expensive than the technology that we were using in the past.
Got it. And I think you're probably going to echo that.
I would have to echo that. Yeah. Especially when you're doing lead acid replacement, having those voltages line up and not having to recertify equipment or go back to an OEM and try to find out if the range can be extended or modified. It just makes life a lot simpler.
Yeah. Good. So I think that's about all I had in terms of the questions for the session. We'll look to the Q&A section to see if there's any questions from the audience. Currently, there's one, and I guess it's related to a different type of battery. It's sodium-based batteries. Do any of you guys have any experience with sodium-based batteries?
I know that there's a lot of work going on so-called sodium-ion batteries, which I'm not that familiar with, but I did work with and have experience with actually sodium sulfur batteries, which are the high temperature batteries that are now primarily used for grid storage. Once upon a time, they were actually trying to make electric vehicles that utilize that technology. And that was, I believe it was invented by Ford Motor Company. And it was, they had a like little van that they were developing back in the early 90s that used sodium sulfur. It's a cool technology until it burned somebody's garage down, which happened twice.
Wow.
Right. I was at one point at Argonne National Labs for an automotive reason, and I got to meet one of the original people who had done the molten sodium battery. So they had encased it in a block of insulated glass, and I was looking at this going, "Wow, you're going to put that on the street, run it down the street at 80 miles an hour, and what happens when it crashes?" Sodium gets real exciting when it touches air and moisture. So it's certainly there's still lots of work in that arena. I hear sodium sulfur coming out of the lab, so there's it's not to say that something can't happen there, but at this point, we would have no plans on trying to implement something like that. It's just not necessary.
Got it. So I guess this is a question from Maria. Do you think the world will completely transition from lead acid to lithium? Or is it going to be another technology that takes over? I guess this is just in general, broad scope.
My personal opinion, lead acid's going to be around forever.
Mhm.
Because it's too difficult to replace it in certain applications.
Yeah, that's the thing that we also find is when we go look at applications, there are lots of applications where you're not going to save money or get better benefit by switching to lithium.
Mhm.
We've tried to pretty well constrain where the most bang for the buck is in switching to lithium. We have cost calculators and all kinds of things. But yeah, the bottom line is it's a well-proven technology. Now, that being said, I know a guy with an electric vehicle from the 1900s that uses iron acid batteries, and they still work today.
Wow.
It's over 100-year-old battery that still works. So, and that is easy to recycle. What is it? 99+% of a lead acid battery is recyclable.
Mhm.
We're not quite there yet with lithium.
Got it.
Yeah.
So there's a question that popped up from Alexander. He states, how does hold on one second. How does pack design compensate for LFP inefficiency at low temperatures or best cathode for low temperatures? I don't know which one of you guys want to take this one on.
So the low temperature operation of lithium batteries can be problematic, particularly on charge. The way that pack design can compensate for that is by using some sort of active thermal management system, say include heaters, or in the case of high temperatures, coolers, things like that. The cost for that is obviously components and complexity, but it can be done. But you don't. What I just mentioned that lithium batteries have an issue charging at low temperature because it shifts the electrode's potential, and lithium preferentially plates on the surface of the electrode instead of intercalating into the electrode. So that's why the low temperature charging is restricted on almost all lithium chemistries.
Would that be the case if you had a true solid state type battery?
Um, if you have a true solid state type battery that you've actually made work, yes, you should be able to charge it at fairly low temperatures, depending on that whatever your solid state electrode
Yep.
light is.
Electrolyte is.
And most electrolytes, solids included, their conductivity continues to get worse as they get colder. So it's still going to have some sort of cold temperature issue without any assistance.
Yep. Paulus,
Right.
did you want to add?
Yeah, we include active anything that we have solutions that operate in freezers, so they contain active thermal management and maintain the cells at such a temperature that you can charge anytime. and that's the way to solve that. So the pack itself can go well below freezing, and we have cooling strategies too in case you have to go above, say, 45C for charging, or some of the new chemistries will do 55C charging. But when you operate it, at these lower and higher temperatures, you are affecting the cycle life. Most manufacturers will specify cycle life right at 25C, and then you can go ask them to look at curves and the cycle life effect at the more extreme temperatures, and it does degrade them. So we try to find that happy spot and balance, heating the battery versus how much energy you get out of it. So,
Right. And then the last question that I see, and I guess this is related to your comment about cycle life, is when does LTO become a viable solution for mobile solution, viable option for mobile solutions?
I could take a crack at that. I did see, was it Nissan Motor Company was showing off an LTO solution for a hybrid vehicle, and their basic justification was that in order to have a battery last the lifetime of a hybrid vehicle and get the 10-year, 100,000-mile warranty, you had to oversize it, and then you had to cycle it within a very small window to guarantee to get that larger life. The smaller the window you cycle the battery, the more cycles you're going to get out of it, essentially. And so they were showing that if they used LTO, they could use something like a half or, almost a third the size battery, and still get the cycle life needed, because LTO is typically quoted at 20,000 plus cycles. So
Or more.
right? So they were showing that they could actually reduce cost in an automotive application using LTO by downsizing that battery. And that, I don't know what's happening today with titanium prices, but I'm sure there's issues there. And this was a show 2 or 3 years ago, before pre-pandemic and pre-conflict. So
Yeah, I agree completely and that's the problem, right? Is titanium is expensive. So if titanium suddenly becomes cheaper than dirt, then that battery is going to be all over the place because it lasts forever.
Yeah. And I think you guys mentioned this earlier. Not only is titanium expensive, but LTO's energy density is very low. I think that operating voltage is 2.4 volts per cell, right? That's the nominal, right? So to be able to get the voltage necessary for these mobile applications, you're definitely going to have to use more of these in series to accommodate the needs of your application. So, but on the flip side, Paulus made a lot of good comments. It's real. LTO is a very, very safe technology, and it has a high cycle life. It's one of the highest cycle lives of any lithium batteries out there.
and the temperature range is huge for it, actually. Yeah.
Yes. So I think that all the comments that the panelists made, it's related. I think it answers your question. If there's anything that you have as a follow-up that you need us to answer, I would definitely answer it for you. Or if there's any other people in the audience that has any other questions, I don't see any open questions at this moment. Feel free. We have about 9 minutes left. Couple minutes, and if not, then we'll end the session. I guess as a closing, John or Paulus, do you guys have any further comments outside of what we've already discussed regarding cell technology?
Now, it was a pleasure to participate in this panel. I think it was a good discussion. We highlighted some of the perils of just assuming that any technology is compatible with your application. So I think it was very good, and I appreciate it. And it was nice listening to Paulus as well.
Thank you, John. Paulus?
Yeah, no, thank you very much. I'll just spend just a minute or two talking about safety. One of the things that people will sometimes say is, "Oh, lithium iron phosphate is an inherently safe chemistry." And I was at one conference where they put that up as one of the biggest sort of lies in the industry. So, any lithium chemistry needs to be managed. Yes, there's levels of safety, but they can all be used safely. Like I said before, the most volatile one is in your pocket. Uh, and we don't have too many issues there. Although, some of the early phones, I personally witnessed a car burn down in a parking structure and burn down the car next to it because of a cell phone. And that was probably the late '90s, right about '99, I think that happened. Um, and so, things have gotten a lot better, membrane thicknesses and all that. So when people look at safety, it's really a system-wide thing. Uh, we have UL ratings on our packs, specifically UL 2580 is for motive applications and forklifts. That that safety rating requires you to send a single cell into thermal runaway and show that it does not propagate. That's the most important thing with the pack design. We've all seen the videos on YouTube of cells propagating, and that gets real exciting. But I've personally witnessed different chemistry cells spew flame and vapor and all kinds of things. And in the right conditions, iron phosphate will do the same thing. But there's lots of things put in place to mitigate that and manage those cells properly. And iron phosphate does have practically the highest thermal runaway temperature, not including titanium oxide. But so really, when it comes to designing the system, it's the easiest one to keep safe. So just to talk about safety. And then, no, thanks, John. It's great hearing from you guys. Now I know where to tell all my friends that want to get lithium battery packs for their golf carts where to go. So it's great to hear there's a drop-in replacement. These neighborhood vehicles are all over the place, and I haven't met a person yet who doesn't want to show off their lithium solution if they have one under the seat. So, no, great talking to you guys, and thank you very much.
Well, thank you both for the participation. It's definitely a worthwhile session that we've had. I hope the audience was able to gain some knowledge on some of the cell trends and the reasons why you're using the technologies you do. Again, thank you so much, and I will be ending the broadcast now. Thank you again. Take care.
Thank you.